Okay, last time we stopped here, right? So in the last lecture we stopped in slide 165. We'll continue from here. So here is another example problem. So probably I'll be using some other approach to do that. Given the meteorological condition and power plant data shown below, determine the maximum downwind concentration of sulfur dioxide and the distance from the stake that it occurs. So meteorological condition: wind speed at 10-meter height E equal to 4 meter per second, sunny summer afternoon. Power plant conditions: Q or E is equal to 151 and the effective stake height H equal to 150. So these are the things given here. Okay, so I'll keep it in few seconds in the screen so you can take a look. Okay, we can move forward. So I'm going to solve it from table 6 to B at wind speed of 4 meter per second. So we get the class stability class B. From figure 631, H is equal to 150, X means this, the figure 631, let's see which one is that. So figure 631, I think this is the one that I'm using, right? This is the one I'm using. So in this case, that means it was H equal to 150, X max is equal to this, and C over Q max I get 7.5 10 to the minus 6 per meter square. Now C concentration maximum would be, if I multiply with this thing, will be 2.8 10 to the minus 4 gram per meter cube is the one of the answer. And at what distance is going to happen is 1 kilometer. That will occur 1 kilometer distance. For stability class of B, A equal to this, B equal to this from the table. Then using the equation, this equation, I get 7.44 10 to the minus 6. They are very close, right? So I get 7.5 10 to the minus 6 by using the graph, and by using the equation I get 7.44, which is close to what we got from the graph. So I solved it using the graph, but I also used the equation to solve it, and I got very close result, right? Now multiplying this one with 151 by 4 will give me very close to 2.8 10 to the minus 4 gram per meter cube. Okay, so I'll keep this one in a few for a few seconds in here so you can take a look and try to understand there. As I said, all of those solutions are also in my the class notes, lecture notes there. Okay, we can move forward. So indoor air quality model, as I said, I'm not going to discuss a whole lot of these things in the quality model. So QCA, these are indoor, what is happening, volume, concentration, the sources coming in, sink, we might have sink, some of them going out through the windows and other things, some of the air pollution coming through the windows also. The sealant in the windows are very important in different cases. So here is the indoor air quality model. As I said, I just showed the equation, how it works, but I'm not going to explain a lot on those things, just a simple representation of this. So here are more equations of those indoor air pollution equations, but as I said, I'm not going to discuss this in a whole lot in there. Okay, the next one is the air pollution control of stationary sources. Pollution control, gaseous pollutants and particulate pollutants. As we mentioned, in the water area, we have two kinds of pollutants, dissolved and suspended. And here it is gaseous pollutants and particulate matter. There are two types of pollutants in there. Gaseous pollutants can be controlled by absorption and combustion. Okay, there are technologies, three technologies that can be control the gaseous pollutants. So here is the absorption. Absorption is nothing but a removal of pollutant gas takes place in three steps. Diffusion of pollutant gas to the surface of the liquid, and the transfer across the gas-liquid interface dissolution, then diffuse of the dissolved gas away from the interface into the liquid. So basically that's how absorption happens. So here is the sum of the absorption. So absorption structures such as spray chambers, towers, or columns are two classes of device employed to absorb pollutant gases. So here are the ones. Looks like, so here are the liquid, we put the gases in here and liquid in here. So when we put the gases in here, gas goes up and liquids are in here. So what they do, the liquid strips the gaseous pollutant from there, and the liquid comes here and the gas gets out there. So there are different ways to do that. Here is the another one. So this is a packed tower, this is a flat tower. They're two different ones. And these are the one shell, different things, packing restrained, things like that. So this is very easy. At some point we might design those, but in this course, just to understand the concept. So this is absorption. Absorption is kind of surface phenomenon. This mass transfer process in which the gas is bonded to a solid. It is an interface phenomenon. It's not internal phenomenon, it's external phenomenon. The gas, the absorbate, gas is called absorbate, penetrates into the pores of the solid. Not really the pores to the surface of the solid is called the absorbent, but into the lattice itself. The bond may be physical or chemical. Electrostatic force hold the pollutant gas when the physical bonding is insignificant. Chemical bonding is by reaction with the interface, if they have any. We don't know. So activated charcoal, molecular sieves, silica gel, and the activated alumina are the most common absorbents. So here are some of the processes that happens when we do things like that. So we have some of the things in here already absorbent bed over here. Okay, so then we push some of the gas from here, pollutant laden gas, this way. Then it goes through the absorbent. The pollutants can be absorbed to the bed. Then the clean gas comes out. So two different arrangement. Looks like this is absorption cyclone. This is a desorption cyclone. So here is the stream. So desorption means something to clean about it, right? To clean. Condensate pollutants, it comes here, condensate, ultimately it cleans up. Combustion is a possible alternative when the contaminant in the gas stream is oxidizable to an inert gas. Typically carbon monoxide hydrocarbons fall into this, even methane. So methane, if you burn the methane, then it could be something, can convert into something else. So that would be environmentally benign. So here is, this is called the flame incineration. So some of those can, in these cases, the burner, this is the burner. So gas burner piping here, inlet, contaminated airstream. We put the airstream over here. It burns over here. So once it burns, then finally, I think the gas comes out some other way. I think, I don't know, it doesn't show. I think it goes somewhere in the top. I don't have it, but that's what it shows. The particulate pollutants, for controlling particulate pollutants, the following control devices are used: cyclones, filters, liquid scrubbing, and electrostatic precipitator. Design of these devices will be done in C4353, but in here I may just discuss a little bit. So it's not, I'm not discussing anything looks like. So these are detailed. Cyclone is basically, it happens due to the swirling effect. And filters, you guys are familiar with the type of filter, right? And liquid scrubbing is sometimes liquid used to do the pollutant. I think we already did the packed tower and other things. This is very similar to that, but the technology is a little bit different. Electrostatic precipitator is ESP, is basically a series of steel plate that has an electric charge. Since the particulate pollutant may be negatively charged, so they have an anode and cathode, so it looks like stick to the anode, and then we scrape those out from the anode and basically take those out from their pollutant and discharge those somewhere else. So we'll go more detailed those things, the four control devices, design and everything in C4353. Also, I think I do a little bit of some of those in, like, say, CE4343, solid waste engineering. And this is 4353 is the air pollution control course. Okay, so I think this brings us to the end of the topic. So and the Like say, if you go to the topic 6 overview, then you'll see the number of homeworks and the due date of the homeworks are in D2L. Thank you very much and good luck with the topic.